In this lecture, let us discuss about basics of Euler equation. We are going to talk about one dimensional Euler equations to keep things simple. As we recall that Euler equations have the capability of capturing shock waves, expansion waves, in compressible flows, and when we compute Euler equations, we can capture these waves automatically in the flow field. So, such numerical techniques which automatically capture the shocks are called as shock capturing techniques, and usually the conservation form of the governing equations should be used in these kind of techniques. Conservation forms are best represented in a form like this, where a system of conservation equations are represented in a compact form by using vectors. The capital U and capital E are basically vectors. So, they have multiple components. If you look at U vector, it has three components, three entities rho, rho U and E t. We have left a blank purposely over here. If you want to extend the one dimensional Euler equations to 2 dimensions, for example, there will be 4 equations in that case to account for, and therefore, 4 terms in the U vector. The U vector is called as vector of conserved quantities, because these quantities which form the different elements of the U vector are essentially conserved in the flow field. They include mass, momentum, energy. If you can identify these structures, that they belong to the continuity equation, the x momentum equation and the energy equation, then you are very easily able to identify the correspondence of these vectors with the respective conservation equations. So, this is a kind of a compact way of representing. A very important aspect of the next term is that you have the derivative operating on elements of another vector, which we call as the flux vector. We are representing it by E, and there are again 3 elements in this vector, rho u square plus p and E t plus p the whole into u, where E t is the sum of internal energy and kinetic energy per unit volume. For a one dimensional problem, of course, v square, that is the resultant velocity square, is nothing but u square itself. In a 2 dimensional problem, for example, this would be u square plus v square. So, if you want to identify the continuity equation, for example, you have to first take the first element of u, apply del t on that, and then add the first term from the E vector after taking a del x of that and equate it to 0. So, this basically gives you the continuity equation, which is essentially by taking the first elements from u and e vectors and applying the partial derivatives on them. So, likewise you can get the forms for momentum equation as well as energy equation, should be straightforward. So, when the del x operator operates on each one of these terms, you do not have terms like this, for example. That means, the del x is not operating on all the terms forming this expression, but rather there is a term multiplied with the del x of u. This gives you a non-conservative form. What will be the corresponding expression for the conservative form? It will be del x operating on u square by 2, because if you do a del x of u square, that will give you 2 u del x, and then the half comes out, and therefore, you get back the same expression. But this is the non-conservative form, while the other one is a conservative form. So, here we are going to use the conservative form, and remember that when we want to capture the shocks, the conservative forms are always more preferred. The solutions in such a case are more smooth and stable, while if you want to use the non-conservation forms, where terms like this may be there in the governing equations, then there could be oscillations or wiggles upstream and downstream of the shock. So, in a previous lecture you saw that certain numerical schemes, when they want to capture the jump discontinuities, develop oscillations. So, there are some kind of wiggles which are formed here. So, these oscillations can be much avoided when you use the conservation forms of the equations. And one reason for that is that in the conservation form of the equations, you see terms that we are using, say rho u. You remember that across a normal shock, for example, we found that rho 1 u 1 is equal to rho 2 u 2. That means, rho u is conserved. But if you look at the density or the velocity, there are jumps in them. For example, if you want to look at density, then it increases abruptly across the shock, or the velocity, it decreases abruptly across the shock. But as far as the flux is concerned, there is no jump. So, the flux is conserved, and the conservative form of the equations are essentially handling those fluxes which are inherently conserved across the discontinuity. So, that is one of the main reasons why they generate solutions which are smoother. Same is the case with, say, the momentum equation part. You remember that from the theory of normal shock or the normal component of oblique shock, you saw the sum of p plus rho u square was constant across the shock, while pressure or velocity or density individually, they were exhibiting distinct jumps. So, having said that, we got introduced to the conservation form of Euler equation, and then we also got introduced with these vectors of conserved quantities and the flux vector. Let us take the concepts a little further. So, we are looking at this equation, and now we are going to change this term a little bit, and we are going to write it like this. So, we will write it as a derivative of E with respect to u, and then multiplied with the derivative of u with respect to x. And then we want to name this as a Jacobian matrix, We will explain what is the significance of that and what is the form of that matrix, and we leave the equation in this form. So, you can understand from what we just discussed that this is actually a non-conservative form. So, in the non-conservative form, there is a coefficient matrix which is being multiplied with del u del x, and we want to find out what that matrix contains. This Jacobian matrix is defined like this. Since you are taking del E del u, where both of them are vectors, that means when you take such a partial derivative, it gives rise to a matrix with 9 components over here. The first row of the matrix accounts for the partial derivatives of the E1 component. So, what is the E1 component? E1 component would be the first row element of the flux vector. Similarly, the second row and third rows will be called as E2 and E3. So, the Jacobian matrix first row comprises of partial derivatives of E1 with respect to the 3 components of U. Second row comprises of partial derivatives of E2 with 3 components of U. Third row comprises of partial derivative of E3 with respect to 3 components of U. And then our intention would be to express each of the components of E in terms of the components of U. So, this is U1, this is U2, this is U3, similarly E1, E2 and E3. How do we take it forward? E1 is rho u, and that can be equated with U2 straight away. What about E2? It is rho u square plus p, and then it is a slightly tedious conversion. We introduce small e t as E plus half u square, while capital E t was already defined as rho times small e t. And then we express E, the internal energy, as a function of p by rho through the equation of state. This is one of the possible forms of the perfect gas equation of state, and thereby you are finally able to take it to a form where you can express p in terms of the different components of U. So, that is what is fed back over here. And how about rho u square? Rho u square can be obtained by squaring U2 and then divided by U1. So, that way you are able to finally express E2 in this form, where U1, U2, U3 all get involved. Similarly, E3, which is by definition the capital E t plus p into U, can be finally shown to be like this, which you can do as a homework. Finally, you will be able to get the form of the Jacobian matrix, which looks like this. Now, by definition, the system of equations that we are handling, that is the Euler equation in one dimension, it will be a hyperbolic system only if this matrix A is diagonalizable. What do we mean by that? What we mean is that we should be able to identify some matrix Q, the inverse of which is also existing, and then if you write down a product of the inverse of Q times A times Q, you will end up with a capital lambda matrix, which is a diagonal matrix. This is what is meant by saying that the matrix A is diagonalizable. Now, the capital lambda matrix again is a very specific kind of a matrix. It is not only a diagonal matrix, but its diagonal elements comprise of characteristic values or eigenvalues of A. That means, if you want to find the eigenvalues of this matrix A, you will find that they are contained in this capital lambda matrix. How does the capital lambda matrix look like for 1D Euler equation? It looks like this. So, there are only diagonal entries, the non-diagonal elements are 0, and you find that they are all real and distinct. When they are so, you can say that the governing equations are hyperbolic in nature. So, the unsteady one dimensional inviscid flow equations that we are handling are hyperbolic in nature, which is seen from the nature of the capital lambda matrix. What do these eigenvalues communicate to you? They give you the slopes of the characteristic lines in the xt space, and obviously at a given point in the xt space there are 3 characteristic lines which are going to intersect with each other. Let us try to see how they really look in the xt space. They would in general look curved, and we are trying to represent them with their slope information, where dx dt is equal to u plus a, u and u minus a for the 3 lines. In general, the u plus a will be sloping more towards the right, the u minus a will be sloping more towards the left, and u will be in between. So, that is how we have drawn it in general. This is also often called as a wave diagram, and we have drawn a wave diagram for the 1D Euler equation here. Now, these 2 waves are often known as the acoustic waves, the right and left running acoustic waves or Mach waves, and they basically are the boundaries of these 2 regions which form the domain of dependence and the range of influence for this point P, let us say. Now, for supersonic flows, all waves travel in one direction, and they would be swept downstream if the flow is traveling in the positive x direction, and none can travel upstream. That is because u is greater than a. Therefore, the term which can become the lowest one, even that remains positive and therefore slopes towards the right. Now, that happens if you have a supersonic flow moving towards the right. What happens if a supersonic flow is moving towards the left? That means towards the negative x direction. Then all wave speeds are negative. That means they will all slope towards the negative x direction. That is how they will look like, and none can travel upstream. What happens in subsonic flows? All acoustic waves can travel both in the downstream as well as upstream direction. Why? Because u is less than a, therefore, u minus a will always be negative anyway, u plus a will be positive, u will also be positive if the flow is moving towards the right. That means, as far as acoustic waves are concerned, one moves towards the right, one moves towards the left. The same thing happens if the flow is approaching from the right towards the left, that means towards the negative x direction. Again over there, one of the acoustic waves will travel towards the right, while the other will travel towards the left. What about incompressible flows? Though here we are basically talking about compressible flows, but can we also bring the incompressible flow in perspective and try to compare? In terms of wave speeds, they are infinite. So, there are no real characteristics, and all regions of the fluid can communicate with all other regions of the fluid instantly without any time lag. The domain of dependence and range of influence equal the entire fluid region. So, this is how incompressible flow can be put in perspective with the compressible flow situation, both supersonic and subsonic. So, you can imagine that from this wave diagram, it becomes clear to you that when you are solving Euler equations in a numerical sense, you have to take extreme care about how these characteristic waves are going to propagate through the domain. And we are discussing the problem only from a one dimensional perspective. So, you can also have multi-dimensional problems where the other directions x, y and z can also be coming into the picture. So, you have to probably look at the different directions separately and try to figure out the characteristic directions and try to apply boundary conditions and techniques in the numerical scheme appropriately, so that the characteristics are properly addressed. We are going to talk about two important problems where Euler equations can be applied without going into much detail, but showing you some typical results. One is what is called as the Swords shock tube problem. We are taking one of the test cases, it is called test case 1. And the problem basically is that you have a shock tube where you have the conditions initially at t equal to 0, where the left and the right states are defined at x less than 0 and x greater than equal to 0 before diaphragm rupture. So, you can figure out that the density on the left is 1 kg per meter cubed, while it is 0.125 kg per meter cube on the right hand side. Both the fluids are stagnant, which is quite obvious, and the pressure on the left side is 10 times that of the pressure on the right hand side. That means, the left side is the high pressure section of the shock tube, that is the driver section, the right side is the driven section, which is at a low pressure. So, once you rupture the diaphragm, then as we know from the shock tube theory that there will be a normal shock formed, which will run towards the right hand side with a contact surface moving behind it at a lower speed, while there will be an expansion fan which will be expanding on the left hand side. And both these wave families will propagate towards the end of the shock tube at both the right and left hand sides. If you want to see the picture in the xt plane, then it looks like this, with the different regions marked in 1, 2, 3, 4. And you can imagine that Euler equation will be able to capture this flow field, because it is able to capture shocks and expansions and contact surfaces. So, when you apply an appropriate numerical model which can discretize Euler equation in one dimensional form like the one we are discussing, in that case after you run the solution for some time by applying the conditions just after the rupture of the diaphragm, you will be able to capture the pressure distribution in the domain in this manner. So, from the pressure distribution you can make out that this is the low pressure end. So, the lowest pressure which was there in the driven section, this portion still remains unperturbed. This is the shock front which is moving towards the right, which will move into that portion eventually and then finally get reflected. There is a sharp jump in pressure across the shock, and then there is a contact running behind the shock somewhere. From this plot it is not very evident, but from other plots we will be able to figure out where the contact is exactly located at this point. And then you can see that over this region you have the expansion fan where the pressure changes gradually. It is not an abrupt change, but it is an isentropic change, and finally it flattens out at the high pressure level, which is that of the driver section. So, the expansion fan will also run into that high pressure region and then finally get reflected in due course. So, the one dimensional Euler equation has been solved using an appropriate numerical scheme, which uses the conservative form of the equations and appropriate discretizations to account for the characteristics, and then finally comes up with this distribution of pressure. So, we are just looking at the final solution. we are showing one more example of Euler equation solution, but here it is a time dependent 2-dimensional Euler equation solution. And what is the problem all about? It is a supersonic flow which is impinging on a wall mounted block. So, you have a rectangular domain here. You can make out that this is the length of the domain along x direction. This is the height of the domain along the y direction. And there is a portion covered by an obstacle. Let us try to mark where the obstacle is. So, this is the obstacle which is mounted on the bottom wall of the section. So, there is a wall on top, there is a wall at the bottom, and this is basically the inflow region, the inflow portion. This is the outflow portion, and you are having uniform flow prescribed here, which is supersonic, and then it is coming and impinging on this wall mounted block, and it forms a detached bow kind of shock, as you can see. And this is a time dependent solution. We often call this as a time marching solution. Which shows you the evolution of the flow field gradually. So, you can figure out that this is at t equal to 0.5 non-dimensional time, and then after some more time has elapsed, it is t equal to 1 and so on, the wave patterns are forming. You can see that this detached shock met the wall on top, got reflected, and then finally after some more time the reflected shock is coming back and impinging on the wall, and then further reflecting back, and then finally leaving from the outflow boundary. This being an inviscid flow, there is no boundary layer formed on any one of these walls, and gradually there are more wave patterns which are forming till you run the simulation to much longer times. This is at t equal to 24 non-dimensional times. And then you can figure out that different parts of the domain are indicated by different contour levels, different colors. So, now I leave it to you to imagine that what kind of a distribution have we shown over here. Is it a Mach number plot? Is it a pressure plot? So, what kind of plot this could be, or it could be something else apart from that. So, now that you have some exposure of the basics of compressible aerodynamics, you also know how to correlate the physics with the computations. You can watch these pictures, appreciate how the wave patterns have formed over time by solving 2-dimensional Euler equations in unsteady form, and then try to argue that what kind of contours are these, what variable has been plotted over here. So, in this lecture we discussed about some very important mathematical aspects of Euler equations, which will give us the appreciation for the fundamentals, and they would form the background of the numerical solution of Euler equations, where different kinds of schemes can be used to solve it. Thank you.